Good morning, members. Last time we stopped on this part here exactly. We stopped on the graph of uniform velocity. That was plotting velocity against time. If we are to remember, this is exactly where we stopped. And today we are going to continue from here. Recall that we looked at a number of terms. We had the distance, we had the displacement, we had the speed, uniform speed, we had the non-uniform speed. We looked at the velocity and then non-uniform velocity. We defined them properly and we even stated the SI units of those terms, and we also compared them in terms of the quantities where they lie. For example, distance and displacement, you remember how we differentiated and what the similarities are. I remember I gave you one similarity and I told you to research about the other similarity. We also looked at the speed and then eventually we looked at the velocity. By the way, we even made some bit of demonstrations on how we can talk about uniform speed and then uniform speed. We also looked at the uniform velocity. Unfortunately, we didn't look at an uniform velocity, but maybe that one will come with the time. So today, I'm going to begin with the differences between speed and the velocity. So that would be like a guiding question. The question, differentiate between speed and velocity. Differentiate between speed and velocity. Just like the way we differentiated between the distance and the displacement, even here you put speed on one side, then velocity on the other side. You give the first difference in accordance to the definition. Even this one would be the definition. So how would we write this? We would say, for this case, that is a rate of change of distance. Then this one would say is a rate of change of displacement. Then the next difference would be about the type of quantity under which they lie. The quantity. So what would we say? We would say that this one is a scalar quantity, that speed is a scalar quantity, and then velocity is a vector quantity. You can add more differences. I'm very sure you can come across them. What are the similarities? Similarity seems to be one only that I have in my head at the moment. The similarity is in accordance to the SI unit. SI unit. They are both measured in meters per second. They are both measured in meters per second. I think I'm right to say that speed and the velocity are both measured in meters per second. Meters per second. Let's look at the types of velocities. Types of velocity. Types of velocities. Types of velocities. Velocity has got about 3 types. One is initial velocity. Initial velocity. Initial velocity is denoted by letter small u. You can see how my small u is. So be careful when you're writing your small u. How do we define it? This is the velocity. This is the velocity with which the body starts its motion. This is the velocity with which the body starts its motion. In other words, it is the starting velocity, is the body starting velocity. What we mean here, you could be looking at the body moving. So the reference velocity with which you start to observe the moving body is what we call initial velocity. So it depends, the body could be at rest or the body could be moving. If it's at rest, then definitely the initial velocity is 0. In fact, let me put a note here. Let me put a note here such that we can easily understand that. One, if a body starts at rest, starts from rest, not at rest, starts from rest. If a body starts from rest, it is initial velocity, u is equal to 0 meters per second. If a stationary body starts its motion, by the way, there is having a body being at rest. If a body is at rest, we call it a stationary body. So if a stationary body starts its motion, then it means its initial velocity is taken to be equal to 0 meters per second. A stationary body has the same initial velocity as a body that starts from rest. Understood? Because the word stationary is the same as static, is also the same as rest. If the observation starts when the body is moving at a certain velocity, say 20 meters per second, then it is initial velocity. U is equal to 20 meters per second. It is initial velocity U equals to 20 meters per second. So that is what we call initial velocity. That is the first type of velocity. 2 is the final velocity. Final velocity, we use small v. Final velocity. How do we define final velocity? We say this refers to the velocity with which the body ends its motion. This hyphen is not supposed to be there, that only. Final velocity refers to the velocity with which the body ends its motion. Okay? Meaning, we can note something just like initial velocity. Number one, if a body is brought to rest, like applying a brake on a car, it comes to rest. The body is brought to rest, it is a final velocity its final velocity is v equals to 0 meters per second. If body is brought to rest, its final velocity is 0 meters per second. You see, that is one. Now, if the observation of a body stops. If a body stops, when I say observation, it means someone is observing the motion of that body. So if the observation of the body stops, stops when it is moving at a certain velocity, say 40 meters per second, then it is final velocity. Then it is final velocity. Let me change the paper. Then it is final velocity. V is 40 meters per second. Then it is final velocity is 40 meters per second. That's right. Then there is what we call average velocity. That is number 3. Average velocity. We say this is the average. This is the average of initial and final velocities of a body. Final velocities of a body. So what are we trying to mean here? Mathematically, we can say this. Mathematically, we mean average velocity. We normally say V is equal to final velocity. Initial velocity is U plus final velocity is V divided by 2. See, that's average velocity. Final velocity, initial velocity plus final velocity divided by time. By the way, try this. What is non-uniform velocity? What is non-uniform velocity? I'd forgotten that. What is non-uniform velocity? You will tell me the answer, by the way. You will give me that answer. I don't know how, but you will tell me the answer for what non-uniform velocity is. Include some illustration to describe non-uniform velocity of an object. You can use the graph, you can use the table to illustrate for me how someone else can understand non-uniform velocity. Okay, so another term, I think this should be number 7, is acceleration. Acceleration, this is the rate of change of velocity with the time. This is the rate of change of velocity with the time. The rate of change of velocity with the time. The rate of change of velocity with the time. The rate of change of velocity with the time. Full stop. Mathematically, what am I trying to mean? We would say acceleration. It is denoted by letter A. Sorry, I'd forgotten. Acceleration, comma A is equal to change in velocity, change in velocity over time taken. Over time taken, I mean the time taken for the change. And in most cases, we always say acceleration is final velocity minus initial velocity divided by time. You see? Wow. We are starting to engage ourselves in some bit of calculations. We are engaging ourselves in some bit of calculations. That acceleration is final velocity minus initial velocity divided by time. Okay? Final velocity minus initial velocity divided by time. I'm using the letters that denote final velocity and initial velocity. I think we know what that means. Now, from this expression, let me first put that aside. From this expression here, that acceleration is equal to final velocity minus initial velocity divided by time. Anyone else can see, any physics student can understand that this is meter per second minus meter per second. You still get meter per second. Yeah? Cows minus cows, you get cows. You don't get dogs. Then divide by seconds. Now, for you who knows indices properly, you would still say, I have meters per second times per second. You just add these two. The base S and S is the same. So the SI unit of acceleration is meter per second squared. So we write the SI unit, of acceleration is meter per second squared. Is meter per second squared. In bracket you can say m s power negative 2. We really forget that? You cannot forget that. I want to give us a simple question here. Simple question here. Are you ready to write? I would have dictated, let me write it. A body has an acceleration of 2 meters per second squared. An acceleration of 2 meters per second squared. Full stop. What do you understand? What do you understand by the statement? What do you understand by the statement? What do you understand by the statement? For you there, what do you understand by the statement? A body moves at an acceleration of 2 meters per second squared. What do you understand by the statement? I've got you. The statement means, this is my solution. The statement means that the velocity of the body increases by 2 meters per second after every second. After every second. That's what the statement means. The statement means that the velocity of the body increases by 2 meters per second after every second. Sorry, the wind is a little bit disturbing me. Yeah. We have another term, that is term number 8, uniform acceleration. Uniform acceleration. What is uniform acceleration? This is the constant rate of change of velocity with time. Constant rate of change of velocity with time. So a body is said to move with uniform acceleration if its velocity changes by equal amounts in equal time intervals. Do you remember uniform velocity? So this also brings us to uniform acceleration, by the way. It also brings us to uniform acceleration. That a body is said to be moving with uniform acceleration if its velocity changes in equal amounts in equal time, changes by equal amounts in equal time intervals. Let me illustrate, like the table below shows the velocity time graph of a student moving around the school compound, just like the first one. We would have velocity here and then time here. Velocity is measured in meters per second. Then time is measured in seconds. When the velocity is 0, the saying time is 0. When the velocity reaches 4, the time taken is 1 second. Velocity is 8, time is 2 seconds. Velocity is 12, time is 3 seconds. If I'm to plot this graph properly, this is the velocity in meters per second against my time. This time is in seconds. We have 0 starting point for time. 1, 2, 3, 4. Then this side, velocity starting point is 0, and maybe we have 4, we have 8, we have 12, we have 16. I'm going to dot this to separate my time intervals properly, and then also the velocity intervals properly. So I'm going to plot my graph, and we see if the accelerations are also the same, just like before. So we can have 0, 0. It's here. We can have 1, 4. It's there. Sorry. We can have 2, 8. Is here. Then 3, 12 is there. So my graph is a straight line that passes through the origin, and that's how we have it. And in this case, we've got accelerations. Acceleration A1, acceleration A2, acceleration A3. We can calculate that in a moment. Sorry for that. I was looking for some more papers to help us calculate this. So let's look at acceleration 1. Okay, acceleration 1, this one here, acceleration 1 is equal to final velocity minus initial velocity divided by the time taken. Now here, when you look at it, the final velocity is actually 4. From here up to there, final velocity is 4, initial velocity meaning is 0. The time taken is just 1 second. That is actually 4 out of 1, and this is 4 meters per second squared. Here, 4 meters per second squared. Okay. Then acceleration number 2. Acceleration number 2, this one here, A2 is equal to also final velocity minus initial velocity divided by time taken. But what is the final velocity? We are looking at it moving from, with the velocity increasing from 4 to 8. So it is 8 meters per second minus 4 meters per second. This one here divided by the time. Time taken is now going to be 2 minus 1. You see, we are subtracting this time here. This one here. When you look at these two reference points here, this and that. Okay, when you look at those two, that is it. We are now subtracting this time now from here up to there. I mean from here up to there, so we get 2 minus 1. And then in terms of velocity, it is now this up to that, so it becomes this 8 minus that 4. Okay, and this gives you what? This is the same as 4 divided by 1, which is 4 meters per second squared. Are you seeing? These two are the same. Then F3, so we are talking about this for time interval. So it is, this is 3 minus this 2. Okay. Then for distance interval, this, we are talking about this 12 and this 8. So what do we mean? Acceleration F3 is equal to still final velocity minus initial velocity divided by time taken. And the final velocity, we said is 12. Initial velocity, we are saying is 8. Divided by time taken, which is 3 minus 2. That is 4 divided by 1. And this is also 4 meters per second squared. Same velocity, same acceleration throughout. The same acceleration throughout. Because when you look at them properly, it is 4 meters per second squared, 4 meters per second squared, 4 meters per second squared. For that particular matter, I think we can even plot a graph of acceleration against time. Uniform acceleration against time. Check. If this is the axis for acceleration in meters per second squared against time, which is in seconds, 0, 1, 2, 3, 4. Now this is 0 starting point for acceleration, 1, 2, 3, 4. We check. For 1 second, the first second, from here up to there, the first second, 1, the acceleration is 4. This is the point plotted. The second, now from here to there, second, this one here, acceleration is still 4. We plot there. The third second, this one now, acceleration is 4. When you draw a line to join these points, it's actually a straight line that passes, that is part of the horizontal axis or the time axis. So uniform acceleration in simple terms, uniform acceleration, when they ask you, this is acceleration, when they ask you to draw the time graph, the acceleration time graph for uniform acceleration, this would be acceleration in meters per second squared with the starting point 0, 0. This is time which is in seconds. It would just be a straight line parallel to the horizontal axis. Uniform acceleration on an acceleration time graph. Okay, that's uniform acceleration. That's about uniform acceleration. Hopefully that is okay for us. Right. Now we can take this note here. We can take a note here. Can take a note here. Note number 1. A body moving with the uniform velocity has 0 acceleration. A body moving with the uniform velocity has 0 acceleration because there is no change in velocity. By the way, for example, if u is equal to 20 meters per second and the velocity doesn't change and v is also 20 meters per second and the time taken in the observation, someone is observing this motion, is 2 seconds, what would be acceleration? Acceleration A is equal to v minus u divided by t, which is 20 minus 20 divided by 2. That is 0 divided by 2, and this is 0 meters per second squared. So any object which moves as at uniform velocity is said to have 0 acceleration. It has 0 acceleration. Okay. That said, another note on that particular case of acceleration is note number 2. Acceleration is either positive or negative. Either positive or negative. In other words, a positive acceleration is an acceleration for body whose velocity is increasing. Are you getting the point? Let me be clear. Positive acceleration. Here, velocity of a body is increasing. Now, negative acceleration. Velocity of a body is decreasing or reducing. Velocity of a body is decreasing. That is negative acceleration. In fact, when a body has a decreasing velocity, he said it to be retarding. He said to be doing what? Retarding. So it is undergoing what we call retardation or decelerating. So it's said to undergo deceleration. And now for that matter, it takes us to another term used in motion. So that term which is used in motion, I think that is term number 9. If I'm not mistaken, should be term number 9. You can remind me, guys, but I think it should be term number 9. Term number 9. Term number 9, it is deceleration. Deceleration or retardation. Retardation. What is retardation? Retardation, this is the negative rate of change. The negative rate of change of velocity with time. The negative rate of change of velocity with time. Negative in a sense that the velocity is decreasing. Because remember, still mathematically, this is what happens. Deceleration or simply retardation is equivalent to negative into v minus u divided by t. That's how we get retardation. Negative into v minus u divided by t. You get it? I want to give a simple question here, and you see example, some numerical question. A body moving at a velocity of 10 meters per second is brought to rest after 5 seconds. Full stop. Find Roman number 1. Its acceleration. Roman number 2. Its retardation. Its acceleration, then its retardation. Now, in your solution, sorry, remember, sorry for that. Sorry. In your solution, you have this Roman number 1. Acceleration, which is A, is equal to V minus U divided by T. Direct. So meaning that your A is equal to, what is the initial velocity first of all? By the way, initial velocity is the velocity with which the body starts the motion. So you started seeing it when it was moving at 10 meters per second. That is the initial velocity here. Then they said the body is brought to rest. So meaning the final velocity is equal to 0 meters per second. We just talked about that. The time taken in this is 5 seconds. So this would mean that our acceleration becomes final minus initial divided by time. 0 minus 10 divided by 5. When you look at it properly, it means that this implies that your acceleration becomes negative 10 divided by 5, which is negative 2 meters per second squared. Yes, that is the acceleration of the body. It is negative 2 meters per second squared. And we say the acceleration can be a negative or can be a positive. An acceleration of a body is only negative if its velocity is decreasing. Remember, it decreased from 10 meters per second to 0. So we said the body has a negative acceleration. Now, what about retardation? Remember, retardation is the negative of acceleration. Yes. So retardation being a negative of acceleration is equal to minus into v minus u divided by t. initial velocity doesn't change. So we would say retardation is going to be equal to negative into 0 minus 10 divided by 5, which is negative into negative 10 divided by 5, and that is the same as positive 2 meters per second squared. So that is our retardation. So members, I think today let us stop here. We shall continue from there in our next lesson. The next lesson, I want us to go and check on how we can convert the units, maybe from meters per second, kilometers per hour to meters per second, like that, such that we can have some few calculations applying it to the common terms that we have looked at, and then after that we shall move to another part or another subtopic of this major topic called linear motion. Thank you so much for today. Bye bye. We meet another time.